In our last video, we tackled the question of how could we approximately find the slope of a curve, even though a curve doesn't have any straight line segments in it. And we did it by approximating the different slopes we got from pairs of points that were near the point we were interested in. And we saw that we got some fairly consistent results, giving us some confidence that we might be on the right track. The question now is there a more systematic way that we can build a kind of slope finding machine? Something that when we give it the particular function of interest and the point of interest, it can automatically process to figure out what the approximate slope is at that point. And that's really what this video is about. So if you think about what we're going to need to build this slope finding machine, we're definitely going to need the input function, whatever it is. In our case, it was y equals x squared in the first example, but we'd like to be able to find the slope of any arbitrary curve. We obviously also need to give the particular point where we want to find the slope, because as is clearly evident, the slope changes depending on the particular point we pick, and that's obviously very different from a line. All along a line, the slope is of course the same. If you look at the table that we built, which is reproduced here on the left, you'll see that we put in various values of x that were closer and closer in to the point in question, in this case 3, in order to get closer and closer to a consistent result, which seems to be about 6 for the slope. And the reason I bring this up is that it's not really the particular x location that we're interested in so much as it is how far away the x location is separated from the point in question. What I mean by that is, what I'd really like to do is recenter the x right at the point in question. And if you think about what that means, it means that the table that we've reproduced here from the last video would look more like this. See, x is no longer the distance from the origin. Instead, we've placed the origin right on the point in question. And so x is measuring the separation either to the left or to the right of the point that we're using as our second point in building a slope, as our second point away from the point that we'd like to find the slope at. Okay. So x now measures separation rather than absolute position. It's not that we had to do that, but it's going to prove useful in simplifying the building of a slope finding machine. So now let's go about building this slope finding machine. We'll start with the simple formula that we have for calculating the slope between 2 points, namely y2 minus y1 over x2 minus x1. The rise over the run. But just to clarify, this means that for whatever function you're interested in, you find its height at x2 and subtract from it its height at x1. Then you divide that result by the difference between x2 and x1. Now, if we're going to use our particular choice of picking a point and then making our second point measured in terms of its separation from our initial point, then it's going to look something like this. Let's let A be the point that we want to find, where we want to find the slope. We'll add on x for our y2 value, and then we'll just make our y1 value the height right at the point. Similarly, x2 is a plus x, mirrored right here above, minus our x1 value, which is a. So if we want to just write that one more time, we'll see that what we really have in final form is f of a plus x minus f of a over what simply now is the measurement of the separation. And all that we're left with is the x. Okay, we've got our formula. Now how will we implement this in the calculator? Well, I think a straightforward way is to assign the function that we're interested in to y1, and then make y2 the slope formula in terms of that function, as well as the point that we've chosen. So for the point that we've chosen, we're going to take whatever value we're interested in. In this case, we wanted x equals 3, and we will store that on the calculator in the variable a. If you're not familiar with how that storing works, we're going to cover that in a minute, so I wouldn't get too worried about that. Okay, so we need to put this formula here for slope into our y2 function. What's it going to look like? Well, it's going to be this. We're going to say that y1, for example, just to use our first case, equals x squared, and then y2 has to capture this slope formula. What is f? Well, it is y1. Our function is whatever we put in y1, and so our slope formula is going to look like this. It's going to be y1 evaluated at a plus x minus y1 evaluated right at a. And then we're going to divide the entire result by x. Let's take a look at what that looks like on the calculator. So the first thing is assigning the point that we're interested in to a. And again, if you haven't done that before, I'll just repeat it here. What we're going to do, we're going to say 3 is stored, see where their store button is, into the letter A. And for that I'm going to write alpha A. I'm going to click on alpha A. When you enter that, you see that A is now associated with 3. If I type A, press enter, it returns 3. Okay, let's go to our formulas. As you can see, for y1 we put in x squared. For y2 we put this somewhat strange looking formula, but again, if you think back to how we designed it, you'll see that it really just says y2 minus y1 over x2 minus x1. I guess it's a little bit confusing because the y2 minus y1 here turns into f, and then that in turn gets represented as a y. But such is life. Okay, so this is our slope finding function. Now let's go into the table setup, and we want to be able to choose the various x values, meaning the separation from the point in question. And so as you can see, I've selected independent as being in the ask mode, so that I can plug in various x values rather than simply have it generate a table of equally spaced x values. So now when I go to the table, you can see that previously I've set up, okay, I'm interested in finding the slope between the 2 points where the one point is the point in question and the other point is 1 to the left, 1 to the right, 0.1 to the left, 0.1 to the right, 0.01 to the left, 0.01 to the right, and so forth until I get closer and closer into the point in question. Of course, when I put in 0, the slope I get gives an error. Now, why is that? Just think about that for a second. Well, what it's really saying is that we're finding y2 minus y1 over x2 minus x1 when x1 and x2 are the same point. We're essentially dividing a 0 by a 0. So it's no surprise that we get an error right at the point in question. But I think what is far more interesting is that we can see this pattern, that the slopes that we get both to the left and right seem to be converging from both sides right to a common value, which obviously I think we're going to guess at that value being 6. So this slope finding machine has reproduced the same results that we had when we built the crude table one calculation at a time, but it found it to even more precision. Well, that's our slope finding machine. Let's just recap what it is that we've built. We have standardized the process of finding the slope of a curve at a particular point by building this machine. And one assumption we made in particular was to recenter the variable around the point of interest. I think that deserves particular attention because it makes the second table much clearer to our purpose than the first table. And then we just take the function itself that we're interested in as one input, and the point where we'd like to find the slope as the other input. And as this calculator table demonstrates, when you look at that, it shows us a ever closer set of approximations, both from the left side and the right side, that seem to settle down in a way that we're not being completely explicit about, seem to settle down to a single value. That is our slope finding machine. Again, I hope you will summarize this entire slide by teaching it to someone else as a way to really cement your understanding.